Thank you for the invitation. It's great to be here. I haven't done an in-person conference in a while because of COVID. I'll be talking to you today about how we use Python to develop a COVID model that was used fairly widely throughout the world. So I know I'm the last speaker before lunch, so I won't go over time. If you're really interested, if you look at me, I might go a little more slowly. If you're really bored and you just type on your laptops, then I might go a little bit more quickly. So that's a nice thing about doing this in person. Okay, so I'll talk a bit about what Covasim is, how it's designed, the performance, and probably of most interest to you, the implementation. And also talk a bit about some of the more meta stuff, not just the sort of Python aspects, but how we manage the team and some of the pitfalls that we had. And we did have a lot of pitfalls, so I'm hoping that we can have a bit of a discussion after that if you have any ideas or can relate. And the graph on the right here just shows what you all know, that suddenly COVID turned from something that nobody cared about to something that people cared about more than food. This was we had to move pretty quickly, and so I'll talk about how we did that. So just a little bit of background about myself. I started off in computational neuroscience. I studied physics and then did cool things like taught robots how to pick up balls. But then starting about 2010, I thought, well, this is cool, but it's kind of having impact for like 50 years down the track, and I kind of want to do stuff that has impact now. So I started getting into epidemiology and public health. And so for a long time, what we would do is we built models to help health ministries decide how best to allocate their money. So we worked mostly on HIV. And so the question was, if you have a, say, $50 million HIV budget, how much of it should you spend on testing? How much should you spend on treatment and things like that? And so I do want to acknowledge up front just the extraordinary team that did contribute to Covasim. So put your mind back into March 2020. No one knew it was happening other than that it was really, really, really bad, as you all know, because you all lived through it. And so just an enormous number of people from all over the world came together to make this happen. So huge thanks to all of them. And a couple of them are in attendance here. So what is Covasim? So it stands for COVID-19 Agent-Based Simulator. I'll excuse you all if you want to go to your laptops and check out the website. So agent-based means that it tracks the behavior of individual people, which is in contrast to a lot of disease models that just look at kind of compartments, like groups of people. Because it's agent-based, it's also stochastic, which means that each run is going to be different. So on a given day, a given person decides whether or not to go to school or go to work or something like that, and that will change their infection risk. And when they're exposed, they might get infected or they might not. It's open source, of course, and it's written in Python, which is why I'm standing here as opposed to the Fortran conference. Do those even still exist? And in contrast to a lot of disease models which are developed by academic groups and very kind of single use, we wanted to make it as easy to use as possible. So, here that means, pip installable. Again, in contrast to a lot of disease models, we did work with professional software developers to make sure that it was tested and documented. So we were trying to prepare it as a proper software package, not just as something to get an answer as quickly as possible. But make no mistake, this was not a software project. This is a public health project. And so we did work with a lot of public health officials, epidemiologists, disease modelers, and other people. And later in the talk, I'll talk about some of the challenges we had of trying to integrate people some of whom had basically no programming experience, but lots of disease expertise, and keen coders who wanted to join the project, but barely knew what a disease was. So just to give an idea of how quickly this Covasim started being used for policy, the first ever release of Covasim was on, I think, the 10th of March, 2020. And by the 12th of March, the governor of Washington State, Jay Inslee, gave a press conference using the output. This is the very first graph that Covasim produced in the background as an explanation for why there was going to be a lockdown. So it's subsequently been used in other places, but almost as soon as it started being used, as I'm sure you're all aware, the denialists came in. I've worked on some reasonably high-profile projects before, but nothing, compared to this. And the level of scrutiny that we got was, in a sense, good. Keeping, it's nice to have some scrutiny, but these were also not good faith actors. So they were trying to find any possible, bug that they could. So this put a lot of pressure on us. Of course, we wanted to do the right thing in the first place, but we also knew that not only did it have to be right, but it also had to have the appearance of being right, which are usually the same thing, but not always. And also, I didn't even know that medRxiv had a comment section, but wow, those can get nasty. So this is where Covasim has been used to date. As you can see, it has been pretty widely used. Quite a few groups in the US have used it, as well as Australia. We have focused a lot on some lower and middle income country applications. So in particular, Kenya, it was used to set some of the school policy, and Vietnam, it was used quite extensively. So in terms of the design, those of you who have experience with disease modeling, which is probably not too many of you, but this will look very familiar. So basically what Covasim is trying to do is one thing, which is calculate the probability that a given person on a given day will change from one state to another. So for example, will they become infected? Will they be diagnosed? Will they die? And the way we do this is with a fairly standard, what's called an SEIR model, which stands for susceptible. You don't have COVID, you can become infected. Exposed, which means you are infected but are not yet infectious. And then I stands for infectious, so you have COVID and you can infect others. And then R is recovered or removed, which includes both when you recover from COVID and when you die. So for the beginning part of the epidemic, this model was fine. But then we had to, of course, modify it because we now know that people can recover and get infected again, as I'm sure has happened to many of you. So the motivating design philosophy for Covasim was common tasks should be simple. So there's certain things you always need to do. So you always want to define parameters, run a simulation, and plot results. And so we really wanted to make this as simple as possible. And so at the top right, you can see the code for doing this. So it's about as simple as it could be. But we're also mindful of the fact that most groups didn't want to just do this, right? Every context is different. If you are looking at whether schools should be open in Nairobi, that's a very different question to flattening the curve in Washington State. And so we wanted to give users as much flexibility as possible to customize it to their own needs. And just to note, these two things are in opposition, so we did have to make trade-offs here. But just to give an example, we were sort of targeting the average policymaker, and in these 28 lines of code is basically a policy scenario that could be used to decide on a policy. Something like, how strict of a lockdown do we need? Can we have restaurants open? Should we have a mask policy? Even with some pretty simple tools and code, you can get pretty far. It's a little different now. The epidemic is a lot more complex, but early on, just fairly simple things had a big policy impact. We also developed a web app, and we learned a lot of things about developing web apps, which the main one being that Python is a lot more fun than JavaScript. So I'll just leave it at that. Okay, so we thought a lot about the design here, and this is the only equation in my talk, by the way. So we felt that there are, again, trade-offs in terms of when you're writing code about where you want to allocate work. So again, the typical academic thing is you write the code as fast as you possibly can, and you don't care about anyone who reads it or tries to use it later. So we wanted to move away from that model and move towards something that was a bit more reusable. And we came up, parallel to the Zen of Python, we came up with this thing that we call the Zen of IDM. IDM is the Institute for Disease Modeling, by the way. And so these are kind of things that reflected how we viewed like scientific academic software development in a way that is reusable and longer term. I want to talk about a couple implementation quirks, which I think might be frowned upon by some of the community here. So hope would be curious to have some discussion about this afterwards. I'll just mention two. One is that if there's only one thing the user could mean, just do it. So if the user supplies a date as a string, use it. Date time, use it. NumPy date time 64, use it. And so because of this, again, this is prioritizing the user. It does make the code kind of messy, but the code would kind of be messy anyway. So for example, we don't do type checking because there's just so many different possible types. And so again, because Covasim is a top-level library rather than something lower down, it's less essential that you have this like ultra rigorous behavior. And it's more important that a user can just put in a date and it does what they expect. Another one is that this is an actual example. So we had a bug, and it took us a while to find it. But generally in the code base, we use what we call semantic indenting, which is that we vertically align things where there's kind of a logical sense to what they do. And so we couldn't figure out why the number of severe cases was being counted incorrectly. And then we went through, we refactored the code, we did semantic indenting, and then this typo, which is pretty hidden in the sort of correct Cap 8 style, it suddenly jumps out at you when you do semantic indenting. So kind of embarrassingly, I think we've caught more bugs just by using semantic indenting than our entire test suite put together. So just something to keep in mind. Another thing I want to mention briefly is our use of a library called Cyrus. Originally it was developed to help us developing web apps. I already told you how I feel about JavaScript. So we were kind of in that intermediate phase where we didn't want to build like a whole JavaScript web app from scratch, but we also needed more flexibility than you could get with something like Plotly Dash or Streamlit. And so there are all of these different sort of choices that you have for doing different things. So do you use matplotlib and mplD3, or do you use Plotly, Altair? So lots of visualization libraries. Also for a database, you can use SQLite or something else. And so what we wanted is just kind of a collection of tools that would all just work nicely together. And then if you decided you wanted to swap out some module for something else, you could still do that. But you could use it as the basis for, just here's a workflow that works. And then if you want to do something custom, like go ahead and do that. So although it was originally developed as kind of a for building these web apps, we found that the core library was actually more useful than the web app part. And so here's an example of a piece of code that generates this like sine wave with some random noise and so forth. So on the left is shown what you would have to do with like vanilla Python. And then on the right is what you would do, the exactly equivalent code with Cyrus. So as you can see, it's about, in terms of the code differences, it's less than half as much code to produce the same result. And again, you don't have to use this. If you have a really particular way you want to serialize some data, you don't have to use the Cyrus save function. But if you kind of just want to save something and you don't care that much and you want something that works fine for 90% of use cases, it's just nice to have something that works. So we leveraged Cyrus quite a bit in the development of Covasim, and we found that it saved quite a bit of time. And Cyrus is just classified as a critical SciPy project, so we're hoping to release it and continue supporting it more. And I also want to talk about something, sort of a main problem that we came across quite early in developing Covasim, which is that we wanted to model these individual agents, but typically in Python that's very slow. So usually when you write an agent-based model in Python, you basically do loops over everything. So for every time step, you loop over every single person, and then for every single person, you loop over every state. So in this example, which is actually a family planning model that we developed that was based on our COVID model, Covasim, we want to have monthly time steps, about 70 years, so this is on the order of 700 time steps, use about 30,000 agents, 30 different states, so that's 1 billion update steps. This is really slow. I love Python, I'm sure you all do too, but this is really slow to do in Python. And so this is an example of what the code looks like. And it looks great, it's super readable. Even if you don't really know anything about like family planning, you can kind of see what's happening here. It's like someone ages, you check if they die. If they're not alive, you like quit. If they're female and they're fecund, you check if they're pregnant. If they're not pregnant, you check if they became pregnant, and things like that. So it's really easy to read this code, but unfortunately in Python it just isn't very performant. So what we did instead is arrayification. And so basically all that's required is flipping the update steps from the time agent state to time state agent. And then this let us use NumPy arrays to do the calculations. And this gave us almost a factor of 100 code speedup. So you can see here that the code is a little less intuitive. It's not this like sort of flowcharty kind of thing. It's based a lot on array indexing. So even though this is an example of kind of the trade-off between like usability and simplicity, that here it's like, well, if it was like 20% faster, we probably wouldn't bother, because for a lot of the disease modelers we work with, like it's much harder for them to read this code than what I had on the previous slide. But come on, it's 100 times faster. Like you can learn how to index an array for that. So this is just an illustration. So for like small number of agents, it doesn't make a whole lot of difference. But then, like as you grow the number of agents, you really see the speed up gains from doing the arrayification. And then just visually, this shows on the right is with the arrayification. On the left is the agent-based one. So you can see that as a user, it makes quite a big difference. We don't have to wait for it to finish. And the other thing that we did to get performance high was using Numba. So I'm sure a lot of you are familiar with Numba. I'm sure there are even some of the, actually, any Numba developers in the room? No, none. Wow. So actually, who is familiar with Numba? Okay, most people. Cool. So you know how Numba works. We found that we didn't really get any speed up unless we did sort of explicitly specify all of the types. And we did also mostly use 32-bit arithmetic, which was pretty cool. Like again, for stochastic models, you don't really care if it's like exactly accurate because it's stochastic. And what we found is that there was like enormous difference, for each function, how much of a speed up there was. So in the first example, this pairing algorithm, I think we got like a factor of 20 speed up by doing it in Numba. Whereas for the second example, which is like the core step of Covasim that calculates the actual infections, we got some speed up, but it was like 30% or something like that. So we found it was really important to test every function independently, and also different data types. Using caching was important, and using parallelization if it didn't call a random number stream. So this just illustrates the difference between the kind of the object-based implementation compared to the array-based implementation. So if you work with agents or anything like that, definitely think if you can do it array-based instead. Okay, so just to close up, I'd like to talk a bit about some different workflows. So there are lots of pitfalls, and I think we fell in every single pit. And so one of the big kind of challenges we had was like between moving too cautiously and moving too quickly. And so IDM is a pretty big organization. Like we're used to like working with agencies like the UN and the World Bank. And if you've ever worked with those, you know that they move like very slowly and very carefully. But on the other hand, we had this like crazy pandemic that was killing people left and right, so we needed to move quickly. But saying something wrong would be worse than not saying anything at all, so we should move slowly. So that was really challenging to navigate. Another thing that was difficult was how much process should we have? So, you know, should all pull requests be reviewed? Well, of course they should, but by how many people? Like, you know, how formal should the test be? Should, you know, someone have to update the change log, you know, even if it's a minor change and things like that. So we definitely had to learn as we were going along with that. And of course, everything's much easier when you have more time. And then kind of the last one is more of a kind of social one, which is that you know, there's that saying, if you want to go quickly, you go alone. If you want to go far, go together. Well, we wanted to go far and quickly. So this was quite challenging. And different people have different working speeds, and so it was difficult to navigate how to move forward as quickly as possible while not moving so quickly that, you know, we lost contributors to the project. And we found that it was really important to find a set of tools that worked well. We started off with Slack because that was the easiest thing, and then we moved to Teams later. And you can see here like just how quickly things got underway. So we didn't have a workplace Slack before the pandemic started, so we went from 0 to over 2,000 messages a day in the space of like a week. And it was also important to be mindful of the fact that different people have different, you know, working styles. So the scientists would want to like post all of the links to the medRxiv papers that were coming out, and the developers wouldn't know what they were. And then the developers would, you know, want to talk about, you know, inheritance and things, and the scientists didn't know what that was. So it took, again, it was challenging to kind of navigate that and try to find ways, you know, to get these different groups to talk to each other. And then of course there are the external, you know, stakeholders. Like you have the governor on the phone. He doesn't, you know, he doesn't necessarily care about the latest medRxiv preprint, you know, or class inheritance. He just wants to know like what should happen. And this is just kind of an illustration of, you know, when the pandemic was declared, you can see that there was like a big flurry of activity right after that, and then we kept updating it, you know, pretty quickly, and then generally it was fairly stable. We moved a lot of the work to our collaborators, and development is ongoing, but it's thankfully slower. And part of that is that we have these different ways of maximizing impact. And so sometimes we do the work ourselves using Covasim. Our favorite mode is to use our partners, so we teach them, work with them, check their results. And then mode 3 is the classic one in the Python community, which is where, again, you just put something on SciPy, let people download it and use it. And that doesn't work so well for disease modeling because the people with the disease expertise are usually not the ones who are downloading things from SciPy. So I'll skip this. We used GitHub for coordination, which worked better for the developers than the scientists. I'll skip. Well, this just shows the activity in GitHub, so you can see how quickly like a lot of people jumped on the project. And yeah, so what did we learn? Avoid technical debt, important to engage local partners, and small decisions matter. Sometimes we would like kind of flip a coin to make a decision, and then we would like regret it for weeks later. So some open questions. I'll just leave this up. What's the future of COVID? I don't know. Don't ask. How do you scale quickly? We found that a small group of contributors did a majority of the work. And how should we build models? So we have this big debate at the moment of should we keep each of our disease models as a separate code base, or should we have like a shared code base and have this kind of like hub and spokes model for that? So if you have any answers for me, let me know. All right, thank you very much.
Thank you so much for that talk. So we have a bunch of questions from Slack. The first one is from Zachary Del Rosario. Curious how you and the Covasim team think about communicating model results even to good faith consumers, given the stochasticity of the model and the fundamental issues people have with understanding randomness.
Yeah, that's a good question, and as a scientist, it's important to communicate uncertainty in your results, and I personally have a lot of feelings about groups who will like present one curve and say this is the answer, this is what it's going to be, and very often that answer is wrong, right? I mean, all models are wrong, some are useful, but most are not even useful, right? But yet, if you're a policymaker and you say, well, and the scientist says to the policymaker, it's like, well, there could be 1,000 deaths next month or 100,000. It's really hard to say. It's like, well, just tell me what I should do. Like, you can't propagate your uncertainty into the policy context. You just have to make a decision. So on the other hand, it's kind of an abrogation of responsibility, as a scientist, if you don't say, well, I think this is the most likely, thing that will happen. So I'd say, in answer to the question, it depends. It does depend on the policymakers. Some are very good at understanding the scientific issues. Others are not so good. But I think as long as you say, if you communicate it with humility, I think that's the most important thing. So still say, this is what we think could happen, but these are all the reasons that it might not happen. And I think maybe not so much at the beginning of the pandemic, but I think certainly by now people understand we don't know when the next variant will happen. It could be bad, it could be, it could be more mild.
Cool. The next question is from Matthew Fikert. Does the web app that the Covasim team made use PyScript and so Pi died?
It does not. So it runs Python in the backend, and the front end is based on Vue.js, which kind of works. We've also been looking at options with Jupyter and Voila and things like that. But happy to discuss more. We did consider Pi died, but it didn't quite do what we needed it to.
From Logan Thomas, how did you test the various pieces of Covasim, especially when this type of pandemic doesn't have any readily available training data at the onset of COVID?
That's an excellent question. I just skip over the testing bit. Most of the kind of bugs that we had in Covasim were like parameter values that were based on a paper that a later paper came out that had a better, more accurate parameter value. So that's very different than the testing in the kind of scientific sense. So most of the kind of testing we did was simply like Covasim was in the hands of a lot of like policymakers and disease modeling groups, and they were all like trying different things with their local data and local context, and then they would like reach out to us and they'd be like, hey, I'm trying to replicate the Omicron peak in South Africa and I just can't get it to work. Like, can you have a look at it? And then we might look at it and it's like, oh, actually we need to revise like how long the minimum period for reinfection is and things like that. So it was kind of, I'd say it's kind of an organic process. We do have a suite of unit tests that cover like pretty much the whole code, but we typically, by the time that a bug was found by the unit test, someone had, who was actually using the pre-release version of Covasim had already like found like, hey, my results don't work. So we found that kind of these high-level integration tests were more effective for catching bugs than the more formal software tests. But it's a great question. I'd love to have a more in-depth conversation about that.
Awesome. Well, that was the time that we had for questions. Thank you so much for a really engaging talk and the conversation afterwards. This is the last talk in this track, and then I think the next is were released for lunch.